Okay. Should we get started? First, to start with, there will be if you manage to stay the entire time of this talk, there will be a raffle in the end where you can win a graphics card from AMD. So please stay. So my name is Johan Andersson. I'm a technical director in the Frostbite team over at EA. And I'm going to do a pretty techy talk about how we implemented the Mantle in Battlefield 4 and in Frostbite in general. So this is the last screenshot you will see in this talk. This is Battlefield 4 running on Mantle. This runs really quite nicely. I think this specific one was on a dual Hawaii board, the 290X, running with very, very stable and nice performance. And just jumping straight into it, this is sort of a high-level comparison of the performance difference we're seeing on this specific config, at least, with one of the highest-end Intel CPUs you can get, combined with real dual 290X boards. And yeah, you can see a pretty significant difference between the X11 and Mantle. In Mantle, we're getting around 120 FPS in this scene, and that's the overall game frame time. It's not just the Mantle rendering that's, improving on that. It's the entire game that's significantly faster thanks to better parallelization. Most importantly, though, I think is not just the average frame rate is extremely high, it's also the minimum frame rate. You have more of a doubling in the actual minimum frame rate here. So playing a game like a fast shooter at a stable minimum 94 FPS, it's pretty sweet. So that's sort of one of the motivations of this overall talk. So when we started working with Mantle for BF4, we had a couple of goals that we wanted to achieve. Significantly better performance, it's pretty obvious on the CPU side. Consistent and stable performance, I mentioned that as well, but also wanted to improve GPU performance wherever possible, using lower overhead drivers and more explicit communication with the GPUs. One of the challenges we had is that we've been working with AMD on Mantle for quite some time, but it is a lot of work to build an API from scratch and build a new driver from scratch and build an entire and fit it into an engine. And we had to do it on a live game as well, because neither of these parts were ready for the launch of our game. And well, we were not ready. We should be a 4 for 5 platforms. I think Mantle for that to launch would have been a bit too much. So we sort of had to work within the constraints of our existing engine design. We didn't want to change too much in all our interfaces, and same compatibility with all the content that we had. And also had to work on a pretty wide set of hardware, from the APUs on the AMD side for laptops to quad GPU type of configurations. And we chose to only focus on 64-bit. First of all, we have very few users on 32-bit still, and that needs to die. There were some things that were sort of not goals for us. We wanted to just bring up a renderer first, not create a completely new renderer adapted to all of these modern different type of designs that we could do, but just learn from it first and then go through it later on. There were also some specific hardware configs that we didn't really care too much about, like a symmetric multi-GPU or truly optimizing video memory. But I'll go through quite a few different components during this talk. So we also had some strategic goals that you may have seen my previous talks about Mantle. We really needed a big title, and BF4 and Frostbite is definitely one of the biggest titles you can get when it comes to PC, when it comes to graphics. And we want to prove that a low-level graphics API is not just a good idea, but it's actually fully possible, and you can actually get really good benefits from it. And try and help and push the industry towards using low-level graphics APIs essentially everywhere. I want to use it on mobile, I want to use it on high-end PCs, low-end PCs, all types of configurations. You sort of need to prove that. And for our own reasons, the reason we're building Frostbite is that we want to build a great foundation for our own games that we're doing. We don't sell our technology, we're building great games. That's the goal of the engine within EA. And Mantle is a good part of that. We want to have a low-level API to base things on. So I'll jump straight into it. So this talk is essentially going through a bunch of different types of areas. It's a pretty wide set of how Mantle sort of interacts with our overall engine and the overall integration that we have. So first part is how we work with shaders. Gennady touched a little bit about this in his introductory talk, Mantle has replaces sort of the traditional graphics shader stage bind points where you have a set texture or set constant buffer with a more of an explicit method that's closer to how the actual graphics hardware works. And in Mantle, this is called a descriptor set. It's essentially a table of the resources that you want to be able to reference and use in a shader. It's just a flat list of images, buffers, and samplers that can be used by any of these shader stages. And in Mantle, we've also gone a little bit further and converted vertex buffers to be able to be part of this. So vertex buffers is just something that's being loaded inside a vertex shader, just as any other resource. It's not a separate fixed function step in the API. And with these descriptor sets, with the engine, when we load the shader, we sort of get to assign, based on the bind spots in the shader, get to assign where they should actually be connected to in the descriptor set. And this enables quite a lot of interesting possibilities. You don't have to have separate textures for your pixel shader or your vertex shader. You can actually share all of them. And in many of our cases, we do that. This mapping is also, perhaps takes a little while to sort of wrap your mind around, but this is a pretty good section in the programming guide for the people that want to work with Mantle. And it's simpler than it sounds. Going forward, we take our shaders that we load, which is actually just the standard DX11 bytecode shaders that we use for our standard PC path. We take them together with this mapping that I talked about on how they map to the descriptor sets and convert them to AMD IL, which is an intermediate language based on a tool that AMD provides called ILC. This is done at load time. The benefit is that we don't really have to change our shaders at all. We can sort of map them to these more modern concepts of descriptor tables. And this tool is also something we have full source over and full control over, although it is a pretty complex tool in itself, and so we're primarily just using it right now. But this is just one way of doing it. You could have shaders coming from some other source, going down to AMD IL, or you could imagine different backends in the future. But this is a pretty nice model for us. So the way we're using descriptor sets in BF4 is actually, it's pretty simple and a little bit naive, but it works pretty well for us. We essentially just have a flat list of resources for each draw call, the resources that we want to reference. And we write that down in a list in a resource table, well, a descriptor set. So it's essentially a pretty direct mapping from how set texture or set constant buffer or set input stream or anything like that worked in DX or in OpenGL. And this is not the only way of doing it. This is just a very, very simple, basic way that we choose to do it. And we have one giant descriptor set, one giant table of all the resources that we can possibly reference within the frame that we're dynamically writing into completely every frame. And we buffer that one and sub-allocate for each draw call. And it turns out that we have around 1,500 of these resources being referenced in the frame. It's actually less resources. This is the amount of things that each draw call is referencing multiplied up. And just writing down 15,000 references to a descriptor set turns out to be really, really fast, even for us. So here's an example of how that can look like. So yeah, you begin with your descriptor set. That's essentially just mapping the memory, making it accessible. And then there are 3 different types of functions, depending on whatever resource you are, to write down a slot to this descriptor set. And then in the end of the frame, we unmapped this descriptor set. This is an opaque API. We don't have the exact access to how the descriptor sets are formed in memory, but we don't really need to at this point. I guess in the future, hardware may evolve to be more standardized in how they treat descriptor sets, and it could be exposed, but we don't have a major need for it at this time. It's still a massive benefit over what we're doing in other APIs. Going forward, though, there are plenty of use cases that we can do if we want to significantly increase the amount of draw calls we're doing or further reduce CPU overhead. For example, I said we're writing down all the resource references dynamically here, and that's not really needed. Most of our draw calls reference a pretty large set of static resources. Well, actually, which textures that the artists have set up for an object and things like that. I think some of our most complex shaders reference around 40 different textures, and that could just be its own resource table, a descriptor set. And that's a much better use case that would significantly lower performance further. And you can also avoid duplicating even more resources between the different shader stages. So I think going forward, we'll probably do a little bit of work here to improve this further. And you can actually nest these descriptor sets because you can only bind 2 of them for each draw call, but if you want to use 5 or 6 of them, you can nest them together, which makes it possible to have different update frequencies and things like that. Moving forward with the shaders, so there are a couple of different types of pipelines, the compute pipelines and graphics pipelines. So in the compute pipelines, there's sort of one-to-one mapping between a pipeline object and a specific compute shader. And these shaders are very simple. There's no really state needed for them. These pipelines can execute in parallel with the overall rendering. And in BF4, we have around 100 different compute pipelines. That does not mean we have 100 unique pixel shaders that do different, no, not pixel shaders, compute shaders that do different things. We do generate different permutations for some of them. But it's a very, very simple fit for that. For graphics pipelines, it gets a little bit more complicated. In Mantle, all of the different shaders for the different stages are combined together into a single graphics pipeline object together with important graphics pipeline state. And in BF4, when you do all this combination for a single level, we have around 10,000 graphics pipeline objects. And it turns out that that's approximately 25 megabytes of video memory, which sounds quite a lot, but, well, it works. It's not really a problem. The video cards we're targeting have at least a gigabyte of video memory. And we could optimize this further because not all 10,000 of those will be referenced within the same frame. So we could have a smaller working pool of sort of active graphics pipeline objects to have a more reasonable set of in memory. But yeah, it works. But there may be some differences there for different engines. One of the really key things that we're after, and Gennady touched on this also, why we want to have these single graphics pipeline objects is that creating a graphics pipeline and creating the shaders for that is a really expensive operation. We really never want to do that at runtime. We want to do that during load time. And we've seen that creating a single graphics pipeline takes around 10 or 60 milliseconds, which is fast in itself. But if you have 10,000 of them, or even if you have a single one that you're creating during rendering of your frame and takes 60 milliseconds, that's a pretty significant stall. In Mantle, we could take that stall on a separate thread compared to DX or GL, but it's still not ideal. So we just go wide during loading and create all these things. And that avoids a significant amount of the runtime stalls that we've seen before. But as mentioned, you need to know some of the graphics pipeline state when you do this, the primitive type, the different render target formats, the blend modes and things like that. And this is quite highly dependent on your engine, but it can be not fully trivial to know this state when you load your shaders and you're working with them. Turns out for us, we were a little bit worried about this, but it turns out that it actually was a pretty good fit for us. We have some separate code where we actually have quite a lot of context about how shaders are used in different contexts, at least the ones that we have huge amounts of. So we were able to sort of prime and preload around 99.9% of our shaders, which is really nice for. And this is an important thing to consider when designing for Mantle and low-level graphics APIs. As we have these pipeline objects, we can well, it actually takes quite a lot of time to create 10,000 of them as well. So to reduce loading time, we essentially just cache them both in memory and on disk. We have a simple 300 megabyte flat database, nothing fancy, and a simple policy on that and compress it. And if the user upgrades their driver or if they change their graphics card or something like that, we will just discard the previous one and generate a new one, essentially. And usually they don't really notice it. It will be a little bit longer loading times the first time. So that was a bit about shaders, and then on to memory. Memory management is something that's very explicit in Mantle, which is a really good thing. And Mantle, the drivers expose different types of memory heaps with very different types of characteristics. Here's an example that I had on my Windows 7 machine with 16 gigs of RAM and a Hawaii board with 4 gigabytes of memory. So it reported 4 different heaps for me. It could be different here in different OSs or different types of configs or future drivers potentially. These layouts can be different. But you can see here, you see if it's local memory or if it's remote memory. So this was a discrete GPU. You see different types of caching flags for CPU access to it. And there's also a bunch of performance characteristics here. These are not really exact numbers, but these are more for comparisons when prioritizing which heap to select, because it's up to the user when creating graphics objects to select which heap they want to use for their textures. Is this a dynamic texture they're updating a lot or reading even from the CPU? Perhaps it should be in system memory and probably in the one that's, if you're reading a lot, in a cached one, for example. So you have this as an opportunity here, and the driver can also, well, it suggests heaps for the common objects, so you can't just go by that if you want to. You may also notice I have 16 gigs of RAM and 4 gigabytes of memory here, but these sort of, if they add up, it's more. So these are actually overlapping at the same time. So you can actually allocate more than this if you want to. This is more of a model to get a good understanding of how the hardware looks like. And in Frostbite, we sort of map them and call and sort of find these different types of heap depending on topologies and call them something that is quite similar to how we've been using it on console. So we have a system shared mapped pool or heap rather, which is memory that is CPU memory that is visible for the GPU. So it's write combined, it's fast to write to, and we actually map this all the time. So we can just write resources into it at any time from the CPU very efficiently, very simple. There's a system shared pin pool, which is more cached on the CPU. We don't really use that one too much. It does exist. And then video shared, which is for larger resources like potentially descriptor sets and things like that you want to write to on the CPU efficiently, but the GPU needs to be able to access that efficiently also. And I think there's a cap on 256 megabytes on that one. And this is something you ideally should not have mapped persistently all the time, because the Windows memory manager may choose to move it back. And then there's video private, which is like the traditional video memory that GPU is the only one that has access to it. So you store textures and render targets and those type of resources that the CPU does not really need to have access to. Another part of this memory management is that the Windows memory management does need to know which memory objects you're using. It can't be derived automatically inside the graphics API. Or rather, we on going with the Mantle design philosophy, we can do a better job on within our engines and do this quite efficiently ourselves. So you need to, for each command buffer, you need to specify which memory references are used. This is not very difficult to keep track of, but there is a limit here also. You can max have, at least in the drivers we've seen, around 1,700 memory references. So you can't have unique memory allocations for, thousands and thousands of textures. There will be, first of all, be quite a bit of overhead for the kernel to go through that to make sure everything is resident before the GPU can render to it, but it also would be slow and fail if it's too many. But this is not too much of an issue. When we gather up the memory references, you have to also sort of specify if you have read-only access or read-write access to it. That's also just a hint to the Windows kernel on how it should treat memory if it has to page it out, essentially. One thing that both this limitation of 1,700 memory references gives us, but also because, it's more efficient, is that we pool our memory. So we use these heaps, and we have, sub-heaps essentially within them, where we allocate anything from 1 to 32 megabyte chunks of memory, and then we sort of manage memory within that ourselves. It's not as elegant as this is on consoles, perhaps, where everywhere we have to reference a memory, we reference a GPU memory handle together with an offset instead of just a pointer. Hopefully in the future that can change, but it's more on the OS level. Fragmentation can be a little concern here, and in order to solve that properly, you could just use GPU virtual memory also and map individual pages back and forth. We're not doing that today, but we probably will going forward. But the memory pooling is a pretty good optimization in general that makes us references a lot less memory objects than what a traditional driver would do, because we have more high-level knowledge on what we're doing, and we can tune that more fine-grained. Then the dark side. If you overcommit on video memory, if you have a 4 gigabyte graphics card and each frame are referencing 5 or 6 gigabytes, there will have to be a lot of swapping going on here. And even if you have exactly 4 gigabytes allocated, there may be other applications using memory in the background there. And that can lead to some pretty significant stalls when VidMem has to move memory back and forth and page it in and out to move the system and the video and the GPU. And this was actually one of the biggest issues that we ran into quite late in our development, when we had everything up and running, and trying to tune this and figure out solutions for it. So there are a bunch of pretty basic recommendations for it, though, to balance your memory pools to make sure you don't have just giant pools of huge amounts of memory divided up in a pretty nice way. Use the read-only references that I told, and also use memory priorities on individual pools. So we have a couple of different priorities. Mantle supports 5 right now, so we have a pretty simple mix here, and this is based a little bit on what the DX drivers typically do also. Like render targets with MSA, you really do not want them to be paged out, and they're usually quite big, so very high priority. Ordinary render targets, USVs, also pretty high priority. And textures, normal priority. We have lots and lots of them, and they may have to be swapped out. And then on the lower sides of just buffers, essentially, that sure, we don't want any of this to be swapped out, but if it has to do something, yeah, swap out our meshes. That's better. But for best results, of course, there shouldn't be any swapping. And this is sort of one of ideally, you should just design your engine and your game workloads so you never overcommit on memory. And here you actually know, in Mantle, you know exactly how large all the resources are, and you know the individual heaps. So you could manage that yourself by restricting streaming pools or capping at different types of quality levels or prompt users, or there are tons of different choices here. You can, as you have asynchronous DMA, you can also transfer memory back and forth yourself to make sure that you're not overcommitting. I do think, though, that going forward, hopefully, sort of the Windows memory model can improve in this area. And then what you're using this memory for typically is for resources. So resources, just as memory, is something that's also explicitly handled and controlled by the application. You control and manage the lifetime of all resources, so you have to make sure that you're not having the CPU write to a resource that the GPU is currently rendering, unless you're after some very specific non-defined behavior. But this is pretty familiar for us, at least, because we've been working on the consoles for a long time, and this is exactly what happens on the consoles. This is actually the model we prefer because we have a lot more control and higher level knowledge. The thing that is a little bit different than consoles, though, is multi-GPU. Here we can have multiple GPUs having their own memory, but it turns out that it doesn't really make it too much more complicated in this case. So as we have high level knowledge of how we're using our resources, we've chosen, just as we've done on the consoles in the past, that keep track of lifetimes on a per frame granularity. You could do it on a much finer granularity or with explicit fences everywhere or different types of per command buffer or something like that, but we chose per frame. It's very simple. So when gameplay or streaming system want to destroy a resource, it's not immediately destroyed because the GPU will have a few frames probably pending at the same time. So we just queue it up, that object or that memory for defer the destruction or freeing of that. And then once the actual command buffers for that frame have finished executing, we can pull a fence on the CPU and check for that, and then we actually do the actual destruction. So this is not really that complicated, and it helps. Though for some resources, we have a lot of tiny constant buffers, for example, between all our different draw calls and small memory objects here and there, and things that are like buffers and images that are transient, that exist only for the specific frame, and you just want to write down some data. So on the consoles, we've been using for a long time linear frame allocators, and so it was a natural fit to use that for Mantle as well. And so we essentially just have a few chunks of a couple of buffers that we maintain on a per frame basis and just write linearly into them from any thread, really, and then access on the GPU. That allows us to simply not have to care about the actual lifetime of that. That's handled on a higher level, and it's also really, really fast, very low overhead in doing this. It's just writing memory. There's an alternative, of course. You could use ring buffers for some engines that may be more important and more powerful, because you can then if you run out of memory, instead of allocating more memory, you can drain the pipeline. So if it's important for you to be at a fully fixed memory memory budget, then that can be better. But then you also have to be able to flush your entire pipeline at a specific point, and not just when the frame is actually done. So we didn't go that route. It was extra complexity. And lastly, an important detail about resources and texture specifically is that the Mantle exposes if the actual texture or image resources are tiled or linear. So tiling resources is extremely important for the GPU memory access of them, and some formats can't even be linear, like the block compressed formats is GPU limitations there. On consoles, we handle this very easily by essentially just taking our texture assets offline and having a data conversion pipeline that tiles them offline, so we can just load them straight into memory, because we know the exact tiling formats of all resources, and we have had this process in place already, and we just create unique resources for each platform. With Mantle, though, These tiling formats, even though it's explicit that you tile or not tile, the actual formats are opaque at this time. And they can be different between different GPU architectures, between different image types, or potentially between driver versions of if they select different approaches here. So we tile our textures using just essentially DMA upload from when we load it in the system memory into video memory. That DMA will automatically tile it during uploading, which is really, really fast and free. So going forward to command buffers. So command buffers are the sort of the atomic unit of work that we dispatch to the GPU. And one of the key differences of this is that the actual creation of the command buffers and execution or submission of the command buffers is separate, fully separate. There's nothing like in GL or in DX where you essentially have some type of a primary or immediate context where you do drawing commands to, and the driver or implementation under the surface will decide that could decide at any draw call or any state call for that matter to flush the pipeline. Here, that's an explicit decision, and this turns out to be a bigger difference than one might think actually, because all of these things with resource synchronization and setup, it becomes significantly easier when you know that you can write to a resource and it will not magically be used before you actually submit it. So we submit all our command buffers in the end of our frame, so we have an entire frame for us to fill in data in various ways. And in typical B4 scenes, we have around 50 command buffers per frame. And this is a balance between the submission overhead, which is related to the amount of memory references you have, and also what type of CPU load balancing you want to have. I think we're targeting primarily quad and hexa-cores type of setups, and 50 command buffers give us a pretty nice split there because they have quite different sizes depending on how many draw calls they contain also. And an interesting point about command buffers is that, at least in Frostbite, we have two really very different types of sources of command buffers, or different types of rendering systems, you could say. One is our overall world rendering. This is us rendering the world with tons of objects. There's lots and lots of draw calls, and this is something we have different types of viewing frustums, and we know all the world data up front. And during this rendering, which could be rendering to G-buffers or rendering a plane reflection or rendering any type of view in the world, essentially, all the resources, except for the actual render target we're rendering to, are read-only. It will only consume, it's traditional rendering, would only consume textures and buffers and stuff like that we've set up. So we can generate these command buffers in parallel very easily up front each frame. And we just kick off a lot of jobs, and they are out of order, they're just generated, and then later when everything is generated, we submit it. On the other hand, though, for the rest of our rendering, which is actually quite a significant amount of components, is sort of, we have something a little bit similar to more traditional immediate rendering. We have a single thread, because this is all the setup that we're doing. And for example, doing clears or setting render targets, doing lighting, various post effects, and virtual texturing, or dispatching different compute shaders. This is more of a serial manner for us. We manage a lot of different types of resource states. If you're rendering to a texture, or texturing from a texture, and we interact with with the different graphics, compute, and DMA queues here. So for us, at least, and at this time, this is sequentially generated in a single job. We simulate a little bit how it looks like in DX here. But I think it's really important to consider that most end users, I do believe, have these two separations. It's very different things from rendering the world from rendering your entire post chain or something like that. And there are different requirements on these. So one thing when this becomes a little bit more visible is how you prepare resources and handle resource transitions. So Gennady talked about this, that the preparation of resources is essentially an abstraction level in the driver that exists in order to hide architecturally specific things, like tracking hazards and driver-specific caches and compression flags on individual resources. There are a bunch of specific ones that AMD have, and there are different ones that the other vendors have. And on the consoles, or at least some of the consoles, we handle all these things very explicitly. But we don't necessarily need to. I think the Mantle has found a pretty nice sweet spot between having these exposed without having them completely in our face. On the console, of course, we want the absolute full performance, but on a PC, we want to be able to run on tons of different types of architectures. Some examples of this is that you need to be able to transition from rendering to a render target from texturing to it, or if you had a compute shader that's been writing to a small buffer and then you want to use that as a draw indirect arguments. These are explicit operations that you will tell Mantle, and nowadays Mantle have a really strong validation layer to track all of these things, which makes it easier for us as developers to make sure we're doing the right thing. And there are a bunch of different ways of managing these transitions. So one very simple approach, and something I would recommend to start with, is to essentially just generate one command buffer at a time in order and sequentially, and then it becomes quite easy to just transition resources as you want to do more different operations on them. This works, but of course it's limited to a sequential manner typically on a single thread. The stuff I was describing with our world running is that we actually go out of order and we want to generate multiple command buffers because we want to use all of the different CPU cores. There it gets a little bit more complicated how you track different state for that. Perhaps you want to track it per command buffer and then fix up when you actually know the order between the command buffers. And one could also see a couple of different hybrid approaches on this. And what we're using in B4 is actually, or Frostbite is actually a bit of a hybrid. So we keep track of which state a resource is for that specific resource. So it's only one state we keep track of. We don't care about the individual sub-resources, like if it's the specific map maps or array faces. We manage to keep track only on a resource level. Then our immediate rendering, this sequential part that I mentioned, that's actually the one that's transitioning resources as it goes. Very quite simple there. And our out of order world rendering that generates tons of command buffers, that one does not actually need to transition that many states. It will write to this memory, to its render targets, but that's already set up because we know that we're going to execute a command buffer that renders a specific render target. And the rest of the world is read-only, so we essentially just use the read-only state for the graphics pipeline as default for our resources, make sure the resources are there. So when we're actually recording command buffers, we don't have to care too much about this, which simplifies things significantly. Though if one would have a little bit more general pipeline and not this type of split that we have, then one probably have to go a little bit further. And if you'd start doing even more parallel command buffer generation, the tracking would have to be a bit more complex to handle that. Another part of the command buffers are the sort of the dynamic state objects. So for the graphics pipelines that I mentioned earlier, they are associated with pipeline state and static state that they're actually compiled into them. But there's also a bunch of states that is still exposed as dynamic state blocks, a little bit similar to how DX11 exposes them, but they're different objects here. And you don't have things like DX have, you can set your stencil reference, that's not part of your object, that's just a loose parameter because it goes straight into straight into the driver to do something with. In Mantle, you only have state objects essentially. And we were a little bit worried about this starting out. You have objects similar to this that have a bunch of settings in them. But it turns out actually for our use case, it was very easy to manage these things. We pre-create all state objects that we can, which is not all of them. There's a couple of them. We know, for example, all the different blend modes we'll ever be using, and it turns out there's not that many different blend modes. We just pre-create all of those states. Some of the other more dynamic combinations, like the one I'm showing here that has the depth stencil state, we don't know the exact depth bounds that will be set on in every case, so we dynamically just create them on demand and store them in a hash map. And surprisingly, we end up with only 100 state objects in the entire engine with this, which is quite nice. Though it is still possible to end up with lots of them, because, for example, the object I'm showing here, that bounds is floats. And if you would create all different float permutations, well, you probably run out of memory for that. But there's really no need to cache or store everything here. You can, again, maintain a smaller working pool of state objects or recreate as needed for the specific frame. You're in control over these objects. You're in control over the lifetime of them. So as long as you don't change these objects while the other command buffers are in flight, you're fine. So we created all of these command buffers, and then we want to actually submit them. So what you submit command buffers to are the queues. So the primary queue is essentially, or is the primary queue that we're using is the universal queue. We can do both graphics, compute, memory transfers, presents, everything. We're also using the DMA queue and the compute queue in order to essentially improve performance. The DMA queue improves performance by just offloading work, memory transfers, pretty simple operations. Compute queue can improve performance by utilizing free sort of idle ALUs while you're doing graphics, like rendering shadow maps. And if you have multiple GPUs, you just get more queues, which is a nice model. And the way these queues work is that any command buffers you submit, you can submit from any thread really, any command buffer you submit will be executed in the order of submission. to a specific queue, but if you submit to different queues, you need to synchronize across them, at least, well, if there are dependent operations. So in this example, I'm doing a bunch of work on the graphics queue, and then I'm signaling a semaphore object, a GPU semaphore, which is signaling the compute pipeline that's been waiting for this operation, and that tells it that it can execute the compute work that's subsequent for it. And then once the compute work is done, it signals back that it actually is done. So these queues, semaphores is something we're explicitly setting up here, and it also works across multiple GPUs and allow us to sort of fork and join within the different queues, which turns out to be quite important for our use cases. So we started out using quite a lot of different explicit semaphores, mostly internally in our renderer to track the different types of transfers we're doing in our rendering abstraction. And it's definitely possible, and it works, but it got a little bit error-prone with having lots of different semaphores and queues, and kind of difficult to know exactly what's going on. So we switched to a model. This is just a logical model, essentially, of representing these semaphores and different queues as more of a GPU job graph. So that looks a little bit more like this. So it's essentially the same code. We just define it a little bit differently. So we just have a long list of command buffers, and each command buffer is essentially a GPU work unit. And in our representation of it, it has a list of dependencies, which are other command buffers. And these dependencies need to be executed first before it can run itself. And then under the surface, we set this up through semaphores automatically here. And this is a fairly minor change, but it became a lot easier to work with and debug and visualize, like this nice graph here. And it's really extendable for us going forward when we're working with multiple GPUs in a sort of different type of manners there. So we're pretty happy about that. And some of the other actual use cases that we're doing on these other alternative queues are things like asynchronous DMAs. And in the test cases we've had, it turns out that the DMAs are typically faster to use for quite large transfers than doing it on the universal context. So it's even just doing blocking operations on these DMAs can actually be faster in our experience. But there are restrictions on different types of alignments, and that is a little bit specific for different GPUs. So you also have to be able to support falling back on doing the copies on the universal queues. So one use case is that we do create our streaming systems, create a lot of resources, both during load time and during actual gameplay. And those resources have initial data that's being loaded into a system memory copy, and we need to get it over into our video private memory. So we do queue up an asynchronous DMA operation for that to not stall the graphics work. And we make sure with our semaphores and dependencies that it's guaranteed to be done before the actual rendering of that command buffer for that frame will be done. And in multi-GPU, another use case is that on some specific settings and specific high resolutions, you have to manually copy the frame buffer between or the final back buffer between the GPUs. So there's one GPU that owns the actual display and another one that has been rendered the frame. So we manually copy it over between them. So that's a peer-to-peer GPU DMA, asynchronous DMA transfer. And going forward with compute, in Frostbite, we have quite a lot of different types of compute shaders that could run in parallel with our graphics work. Things like HBAO is just using a Z buffer and doing quite a lot of different passes with that, and blurring is quite independent. And the thing we chose to focus on initially was our tile-based lighting. So our tile-based lighting is something we've had a while since BF3, but we improved it further. So it's essentially a sequence of 3 sequential compute shaders that are running. One that analyzes the Z buffer and creates the min-max Z tiles, essentially. One that calls light sources, and one that actually applies lighting. So the input there is pretty simple. You need a Z buffer and you need a G buffer. And the output is pretty simple also. You need a UAV access to our HDR texture. And we actually have quite a few different rendering passes in the game that are completely independent of this. So when we're rendering our shadow maps, we're not using the main HDR target. Rendering our reflections or distortion, all those go to different render targets. So we can schedule that separately, which we do through the dependencies here of signaling explicitly the compute work and then later synchronizing on it before we actually need to use this HDR texture for graphics operations. And this worked quite well. We sort of had to manually set up the resource states for this and make it quite explicit. It's not something we could sort of automatically detect at this time, but something we'll look into a little bit more. There's also some gotchas of these. You have to sort of transition and prepare the resources on the queue that last used it, which turns out it requires some changes there. And we've seen some nice performance in this, but it's around 80% faster in some cases of essentially free utilization here. But it's not very reliable. It's very dependent from each scene to scene, depending on if the shadow maps contain huge amounts of vertices, or depending on what the limitations are, because you're essentially loading work on the same type of graphics, same compute units on the GPU. And talking about multiple queues going forward to multiple GPUs. So for multi-GPU, with Mantle, there's tons of different alternatives here. Multi-GPU is explicit, so you can choose to implement something in yourself. You don't have to wait for an HV to create a driver that tries and automatically figure out what you're doing and try and do something intelligent about that. You have to do the intelligent work instead. So you could do traditional alternate frame rendering, and that's what we're doing in Frostbite, with having 1 to 4 GPUs, sort of roughly the same type of power and memory setup. You can do heterogeneous AFR when, for example, you have a laptop with a small GPU and a big GPU. Not too fond of that setup, but it can be some benefits with it. Or you can split your main frame buffer in 2 or 3 or 4 different splits and render on different GPUs, and then synchronize and then render the rest of the frames. You could also do, and this is something we're more interested in going forward, take this GPU job graph that we have. If all operations of graphics and compute are completely identified and with dependencies, and they're actually split up in a nice way, perhaps with some tiling, you could have a primary GPU rendering everything, things, and having the other GPUs help out on different command buffers for that, and synchronize sort of within the frame. But we're using AFR in Frostbite, for now at least. And from our work with our DX11 path, Frostbite actually supports AFR natively. We don't have any synchronization points within our frame, which is not super easy to maintain, but that's what we've been able to do. And for any resources, like, for example, you've changed re-render an environment map when the weather changed on your level or something like that, and we render it on the GPU, those type of operations we in Frostbite always duplicate for each GPU for subsequent frames, so because otherwise the data would be invalid there. So for Mantle, the way multi-GPU works there for us when doing AFR is that we have to follow a couple of steps. So first, we make sure we duplicate all the different textures and images that we're loading to each GPU, and we sort of hide it internally in our rendering abstraction, similar to how the DX or GL driver does it, but we're in control over this, which is quite nice. And every frame, when we want to start rendering and setting up command buffers, we just alternate which GPU we're going to use, which queues we're going to use for that specific frame. And so we build the command buffers for that specific queue, and also these command buffers references the right essentially Mantle handle for the images and buffers that it belongs to the corresponding GPU for that specific frame. And otherwise, it's not really that much different for it. Another gotcha is a little bit that when we update resources from the CPU, not the ones that we update every frame, but the ones that we update, occasionally. For example, there was an impact on the terrain, and we want to update those specific vertices, and then it should just stay there. We have a version similar to the DX11 update sub-resource within Frostbite, where we get memory for that specific frame, and then we queue up an update for the current GPU, but we also queue up updates later for the other GPUs, so the memory will be consistent on those. But it can't update it directly, because the other GPUs may already be rendering and should be rendering with the old data. So there's some interesting temporal problems you can have there if you don't do this properly. And I mentioned in the async DMA case that you may have to present handling presentation in multi-GPU. There can be some trickiness with it also, have you to transfer frame buffers and things like that. And as a bonus, some things we found out when doing this work is actually, we've always had the problems that multi-GPU is important for us, both during development, and it's important for our end users. I think 5% of BF4 users actually have multiple GPUs, which is not huge, but it is very vocal and very important customers. And we can actually simulate multi-GPU mode within Mantle, within our own code base, even on a single GPU. At least simulate from a development point of view, where verify that we actually are doing all these copies correctly, because as we're managing the memory explicitly, well, we can load all textures twice and simulate that we have 2 GPUs and switch between those resources every frame. You can do the same in DX also by creating multiple resources, but it becomes a lot more explicit here, and some of the more complicated operations like the update sub resource and stuff like that just works. Same with windowed mode. We've always had the issue that we wanted to use multi-GPU for our editor, or just people running in borderless or something like that in window mode, and with Mantle, that works. There are some gotchas depending on how you present the screen and stuff like that, but overall it works, which is very cool. One issue though with multi-GPU, and this is fairly common issue for people playing with multi-GPU, and been quite publicized recently for tons of different games, and IHV's got in pressure on implementing this properly in the DX and GL drivers. So one of the issues we've been seeing also is that, well, if we have these multiple queues and we're rendering different frames, that rendering is actually independent of each other. We can get issues like micro-stuttering because the frames are not necessarily presented in regular intervals. Each GPU is rendering independently and it's presenting in the end of it, and sure, we synchronize to make sure that the presents are in the right order, but they're not necessarily at a very regular frequency. On a single GPU, it would be a lot more regular, but here they sort of can float around a little bit. NVIDIA has a really good sort of video analysis tool where you can check analyze these things called FCAT. That we've been using a little bit ourselves also. So here's an example where you see presents are not really very regular over this timeline. Ideally, you want something more like this, where they are very regular. But in this specific example, the actual frame times are very regular also. And even in this case, if you don't explicitly try somehow to synchronize so your frames are exactly half a frame offset, which is very difficult to do when everything is dynamically changing, you will not really get that scenario. So we do need to do something ourselves to improve on this. And that is introduce some type of dependency and dampening between the different GPUs, and it's typically called frame pacing. So with frame pacing, what we do is that we measure a sort of average frame rate on each GPU independently. It's a pretty short history, like 10 or 30 frames. Filter out any type of spikes that could happen. Usually it does not happen, but it could. And then we essentially introduce a delay on each GPU to sort of force them in to be more regular, the actual presents. So the delays are just before the presents here. And this actual delay time, that's calculated based on this average frame times. And there's actually a lot more to it, how you actually set this up and have the queues interacting and delaying, and it's a little bit specific there. Hopefully this can be hidden a little bit more in a utility library going forward, but it's been an eye-opener to implement. But it significantly improves the frame rate, and, well, actually the perceived frame rate. You may have a really high frame rate without this, but yeah, the micro-stuttering can be perceived to be not very smooth at all. So that was about the main topics I was going to talk about. Have some sort of like final recommendations on how to work with Mantle based on our experiences. So first of all, the validation layer that Gennady and company has implemented is really, really critical tool. When we talked about Mantle from the actual start or having low-level graphics API, this is sort of the thing that makes it possible for everyone, because just going straight to the metal or even just exposing everything and just having us figuring out is not really ideal. It's very useful to work with the tool so you can verify they're actually doing the right thing, because there are a lot of pretty complicated cases. But if a validation tool tells you that directly, it's a massive help. So we actually tag up all our different objects that we have, and the Mantle layer is pretty good at telling you when a resource is which resource or memory range is overlapping or doesn't have the right states and things like that. Also, in our experience, we have a big engine. We have a lot of different types of rendering code for us and lots of different types of platforms. And as we didn't want to rewrite the entire rendering abstraction that we have, we sort of ended up with quite a lot of code for object and memory management because it's very explicit in Mantle. We'd like handling it explicitly, but going forward, we'll try and share that more with your console code, and that would be my general recommendation. Also have some pretty strong abstractions and mechanisms for that in your code base. And the overcommitting, I was talking quite a bit about that. having control over your memory usage, or really thinking about, okay, how should I actually manage video memory properly? Most PC games do not really care too much about that, even in the DX space, and actually suffer from that. In Mantle, you can do a better job, but you can also do a worse job than the DX driver does if you don't behave properly here, which is sort of, yeah, the intention is you have to write good code. Resource states and preparations, having a robust solution for that early on is very helpful. Same with figuring out that your actual design in your overall engine fits with how you know which graphics pipelines you're using. How do you actually, can you actually know the graphics state at that point? If you can't, how would you know that? Because creating shaders and graphics pipelines during runtime is not a good idea. You can do that and simulate a little bit of the DX type of stuttery behavior that you can sometimes get when you have to have other threads creating shaders on demand. That is possible, and it may be good enough for some use cases. For us, it wasn't good enough. We had so many shaders. Also, multi-GPU support may not be important for everyone. For us, it's really important. And it's actually not that difficult to implement if one does it from the start, if one thinks about how you would represent resources that actually can exist on multiple GPUs at the same time. It's a lot easier to do it from the beginning than to retrofit afterwards. And then finally, going forward, well, this was for BF4, our first title on Mantle, so I haven't really gone through the details on exact performance characteristics everywhere, mostly because a lot of these things are very new. Some of our use cases are not fully optimized yet either, but they're working really, really well still. We have multiple waves, some sort of Frostbite game titles pending, because all our games going forward we're planning on having our Mantle renderer in them. And so while we're working on those other titles, we're also want to sort of take the learnings that we've had from working, well, very early on with Xbox One and with the PS4 and with Mantle, and sort of see and figure out what is really the right fit in our rendering layers within Frostbite. See how we actually can bind resources properly and manage our resource tables, and how should virtual memory really fit into all this for the pretty forward-looking renderer. And we have a lot of opportunities with ASIC compute and ASIC DMAs, and same with multi-GPU of job graph use cases for that. I'm also really interested to see how Mantle would behave on something like Linux, especially as one of the main issues we had was memory management. I'm not sure how different the Linux memory management is, but it would be interesting to sort of see how it could fit together. Yeah, that was about for all of it for me. Are there any questions? Thank you.
Hi. Yeah, my question is on the across queue synchronization. So I hope on a single GPU, I assume the signaling is pure per GPU, so it's only involved the CPU, right? Command processor.
No, so on a single GPU, you'll still
you
can still have multiple queues, but you don't have to use them.
No,
correct.
It does not involve going back to the CPU or the driver layer or runtime.
No, so it's the GPU synchronizing or the graphics kernel synchronizing.
No, I'm just trying to make, I hope not, because otherwise, But what about across multiple GPUs? How is the job graph that is oriented for multiple GPU can signal each other queues?
It's actually quite interesting, even though DirectX does not actually have built-in support in the model for multiple GPUs. It's something that's implemented in the drivers. The graphics kernel in Windows has many device support implemented. So the graphics kernel can actually get command buffers from multiple GPUs and manage that and schedule that work. And support synchronization and semaphores internally within that. So the graphics kernel in Windows is handling that actual submission between multiple GPUs.
But the signaling, I'm concerned. Let's say you have one compute shader running on the first GPU, and then your graphics, you have another. You have your graphics shader waiting on a signal on your second GPU. That involves kernel
I guess that would be a better question for the AMD guys or for the Windows kernel developers. But it works really nicely. But I don't know the exact details of how the exact kernel interactions are. But there are really no stalls in these things.
Okay, thanks.
With the DirectX 12 coming out, would that address some of your objections? Would you see that as an improvement over 11?
I would definitely see DX12 as an improvement on DX11, yes. You'll hear more about DX12 tomorrow, I guess. And then we have a talk specifically about that, about DX12 also. And it's definitely closer to what we're doing in Mantle here, but there will be a lot more details tomorrow.
So the following question is, what were they doing so poorly in 11 that made you just abandon it?
Well, we haven't abandoned it. Most of our users are using DX11, and we still have that path and continue to maintain it and things like that. There was one thing. I actually did a talk, I'm not sure if it was here or SIGGRAPH, but quite a few years ago, about even the very basic thing of doing deferred context to record your command buffers in parallel. That was one of the new features of DX11. We implemented support for that before DX11 was even out. We're working quite closely with Microsoft and ISVs, and it has never been optimized or actually properly working in any driver ever. And that was probably 6 years ago or something. So that's kind of disappointing. And that's a very simple thing compared to the rest of the stuff we're doing here. Well, I guess Microsoft switched away a little bit in their focus for a while also on from desktop more on getting the overall ecosystem working. But yeah, we're working with Microsoft as well.
Could you talk a little bit about the API interoperability and if Mantle gives you maybe access to stuff that you might not be able to do in, say, DX11, DX11.2 or maybe something in the future?
Sure. First of all of these things, I think I think everything is available on Windows 7 today, which is really, really nice. Most of our users, I think around 65–70% of our users are on Windows 7, so that's a really important target. And there are things like the multiple queues, definitely not exposed in any way, doing asynchronous compute or asynchronous DMAs. The parallel command buffers does not in practice work in DX11. General overhead or working with memory in a sense more explicitly, you can't really do that in DX. We actually, on Windows 8 and DX11.1, we try and go wide with our writing dynamic constant buffers and things like that. And we get some really good benefits in 11.1 for that, but we still have to synchronize our map calls back and forth. And that's just filling in the constant buffers. The actual command work we can't do in parallel. So there are a lot of features, both hardware and software-wise, that we can't do in DX11 that sort of we wanted to do, that Mantle has enabled us to do. Well, to be honest, we support 5, 6, 7 different platforms in Frostbite, and we have our own rendering abstraction that covers those things, that have adaptations towards the different APIs and different platforms. So yes, most of these things that we implemented, we can implement that target Mantle specifically without changing things for DX11, where we're perhaps a bit more constrained, or OpenGL, which is, oh my God, let's not go there. We have some abstractions that cause us sometimes to write quite a bit of code, because the world rendering I mentioned, that's quite separate from the rest. We essentially have 2 renders in Frostbite, you could say. That's one that handles our world rendering and huge amounts of draw calls, and one that is more like graphics API abstraction, a traditional one. The only reason for that is that we get a lot of opportunity to optimize in our dispatch for the stuff that we're doing for our world rendering. So on PS3, that runs all on SPU and things like that. So it's different abstraction levels. Sure, if you had an API that looked like OpenGL or DX11 and you want to optimize that with Mantle, I think you can actually do that also and still get a benefit, because part of our rendering does look like that, but you may not go the full way. But that's definitely possible also.
Yeah, with such a big difference in performance between Mantle and DX11, if you were to look at like the timeline of what was running on the GPU, do you have an idea of like where those gains came from mostly?
You mean of the performance improvements? How much was the actual? Where was the GPU faster, not the CPU?
I kind of understand why the CPU would be faster. I'm just wondering, like, Is it just more work for the GPU to do at any given time?
No, so for the GPU, there are some things. One is that, yes, we actually are consistently feeding it. That's actually a real problem in multi-GPU, that the CPU is so slow at feeding it work, and you need to scale up and run on multiple GPUs. So you need to have a very, very fast CPU and very low overhead there to actually feed it work. But when it comes to other GPU parts, there are things like the cache flushes and the state transitions that we can do more efficiently together with the driver, because we know how we're using our resources, so they don't have to decompress or compress and flush things as much as sort of a black box approach in traditional APIs would have to. I think that would be the last question, but there's a break, 30 minutes between the different until Dan's Mantle talk, and we can do the raffle thing and see if someone gets an AMD card here. Yeah. Oh. So, oh yeah, here we have a number. So, the lucky person has number 353. That is 059353. Okay, 059353.